for the last section in this unit, we look at applications of where exponential functions and logarithmic functions are used in real life. So we go through a bunch of word problems. And here's just sort of a list. It's quite extensive. There are lots of things that are modeled exponentially. Some of the things you've heard about in the past with exponential growth is like the Richter scale. An earthquake, each time it goes up on the scale, is 10 times more intense than the previous number.
Oh, tornadoes also do that?
I don't know about tornadoes.
Sure?
I'm not sure. I've never, it might be, because a strong tornado is so much more intense than just your average wind. So what we do is we use these scales whenever there is a huge difference between things. Sound, a really quiet sound and a really loud sound have a huge difference, so then that's measured on an exponential scale. So we're going to look at a bunch of these problems. And the neat thing about the grade 12 is any topic could be asked, even one you've never heard of before. They just have to provide you with the formula and explain what the formula is, and then you're expected to know the mathematics behind solving it. So our first formula that we're going to look at is a compound interest formula. And this would be given to you, the letters might even change. They could give you the same formula with different letters, and each of the items will be listed, right? This is your interest rate as a decimal, time in years, number of times it's compounded per year. And sometimes it's just a matter of, can you plug in the numbers into the formula in the right spot? So here, I would like you to look at that formula and just plug the numbers in where you think they belong. I'll put the answer up in a second. So check how you did. Did you put the 2.25% in as a decimal? Compounded monthly, then the n would be 12 times per year. And this is a simple one. You could just type into your calculator. You should check these later with your calculator, or check them if you have time. Can you type it into your calculator correctly? Calculators are wonderful things if you can type them in correctly. Same thing. I'll get you to try to put the numbers in first on your own.
What was the answer?
The last one's answer was $626.03. All right, see how you did on this one? Now, one of the things I put in aside over there, sometimes you have a calculator where your exponent button is this little hat. And then you're going to have to put 2 times 5 in brackets. Some of you would just be like, oh, I just can do that in my head and put 10 is fine. But sometimes you get numbers that you don't want to do in your head. And if you have a calculator where the exponent goes up, it's no problem. You can just do 2 times 5, it shows up in the exponent. But some calculators still show this as you're typing, then you'll need extra brackets. Again, make sure you know how to use your calculator. This is a high calculator unit. It's probably be 1, 2. You should figure out, because on your exam you're allowed to use a scientific calculator, but not your graphing calculator. So if you've been using your graphing calculator all along, you will also want to make sure you find some of these questions, try them on a regular calculator just to get the ease of that as well. Yes. Why aren't we? That's a little complicated question. Used to be that you could, this is a more typical type of question because it's asking you to calculate a time that it would take for an investment of $30 to double. So when we plug things into our formula, you would start with $30 and you would get to $60. And now the time that we're solving for is in the exponent. Earlier on in this unit, the only way we could solve this is to put this into y1 and this into y2 and find out where those graphs intersect. But now that we've learned logarithms, we can solve this using logarithms. Because when solving for an exponent, the idea is I can take the log of both sides. Now, a preliminary step says if you can get the power by itself, your life will be easy. So in this case, can I get that in the purple box by itself using algebra? Yes. I could divide both sides by 30. And I get 2 is equal to 1 plus 0.07 over 12 to the exponent of 12t. Now, how do I solve an exponential equation algebraically? I take the log of both sides. That log of both sides lets that exponent come out in front. And now that that exponent is out in front, I'm going to circle that t. The rest of that are numbers. So if I want to get t by itself, I just need to divide. What do I need to divide by? I need to divide by 12, and I also need to divide by that log. That gets my t value by itself, and then I can solve. 9.93 years. Now this question is fascinating because it says if you had 7% interest and you had $30, in 10 years you would double. Which isn't that exciting because $30 to $60 isn't that much. Okay? But if you had $30 million, it would take 10 years for it to double to $60 million. And that would be kind of exciting. I've been trying. I haven't found any rich person to donate me money. Be like, it's for a good cause. I want to show my math students how this doubling of money works. So I would like you to give me $30 million. Don't worry. In 10 years, I'll give it back. But if it doubles in 10 years, wouldn't that be that'd be a very nice thing. And then I'd give them back their $30 million, but it would have doubled, and I'd have $60 million. What is cool in this question is this step. What's cool about it is that it means it does not matter what amount you start with. The time it takes to double stays the same, right? Because if this was $5 to $10, I could divide and I'd get 2. If it was 20 million to 40 million, I could divide, simplify the equation, and I would get 2 every single time. And the equation would be solved the same way after that every single time. So if you would like to deposit a nickel into a bank account, you find out in 10 years you have 2 nickels or a dime, right? Which wouldn't be that exciting, but it'd be much more exciting, right? So I guess the rich person says, well, you could show them the same thing with the nickel. Be like, oh, but it wouldn't be as exciting. So, second thing that's really cool about this question is that in mathematics there's something called the rule of 70, and sometimes it's called the rule of 72. It is the most simple simplification of the complicated thing we just did. So solving this question requires us to know how to use logarithms. We did all of this math to find out that it takes 9.93 years. This rule is the simplest estimation ever. The rule says, take 70, divided by your interest rate, and it is approximately the number of years to double. What interest rate did we have in the last question? 7. 70 divided by 7 is 10. It's sometimes called the rule of 72. You just use whichever one is easier to do mental math. So if I had 8% interest, I'd use the rule of 72, because 72 divided by 8 is nicely just 9. And if you got 8% interest, it would take about 9 years for your money to double. And it's just an approximation, but it's really, really close, scary close, that it's kind of cool. So again, the hardest part in these questions is just plugging it in. What is it that you don't know? What do you know? Plug the things properly into the formula that was given and solve. And in this case, the p that we're solving for, it's not in an exponent. You only need logarithms to solve if the variable you're solving for is in the exponent. So in this case, you can just divide both sides and get your answer. I'm going to leave the next question for you to do on your own, and we're going to go to the one that is tripling. So just like doubling, it doesn't matter what number you use. The time will take the same amount of time to triple, just like it takes the same amount of time to double. Sometimes this can be a tough part on the exam because you feel like they haven't given you enough information. It just says, calculate the time it would take for an investment to triple, but they don't tell you how much the investment is. So you can choose anything, $1 and $3, $7 and $21. No matter which one you choose, right? Let's say I chose $10 and $30. I want to get this part by itself. So when I divide by 10, I get 3 no matter what. Then you can take the log of both sides. Yeah, so if I borrowed 10 million from some rich person that wants to help my students learn math. That's the idea, right? Now I solve for this. Again, here's the t. It's no longer in the exponent, so you can divide by the 12 and divide by the log, get t by itself. I could tell them, hey, I'll give you back your money in 22 years. No problem. And maybe I'll even get my students to sign a nice card. That would be a good idea. Yes. It was like with 10 and 30. You can choose anything. So originally I had 1 and 3. Some people put amount and 3 times the amount. Well, what happens when you divide both sides by a it just becomes 3 and 1. So it doesn't matter the amount that you start with. But this can be a hard thing on the exam. If they ask this question, you say, like, I don't know how to start because I'm missing numbers. It's going to be the same no matter what number you choose. Okay, that's our first formula, compound interest formula.
Does that go for double too?
Yeah, they don't give you the values, you can choose anything, because it doesn't matter the time. Quadruple any number, that would work. All right, our next formula involves the number E. Call this the PERT formula, because it says PERT. This is what happens when something is compounded continuously. Now, this never happens with interest rates because people would get mad at the banks if they're like, you mean you're always charging me interest every millisecond? You decide to charge me a little bit? That makes me angry. So, but when things get close to an idea of continuous growth, the number E appears in the question, and it appears in the formula. And you can see a little bit of that some more once you study more calculus. Population, for example, our population is so big that we would say the Earth's population is continuously growing. Okay? We can think of this either very happy or very morbid at the same time. Since the start of class today, very happy news. There's been a ton of babies born. We can look it up. It's like, oh, like probably every time I'm snapping my finger, there's a baby being born somewhere in the world, right? That's happy news. Morbid news, there's people dying. There's people that have died since the beginning of class. So population in the world is always having this. It's crazy. I think I looked it up. It's like over 300 births per hour in the world. It might even be more. So if you think of an hour-long class, it's only 60 minutes. That's like every minute. Babies popping out everywhere. And people dying everywhere. Sad news. So we've got good news and bad news all the time. When things happen that quickly, we tend to say that growth is continuous. And then this formula comes up. And this formula used to be on the formula sheet, and you would have to recognize that any question that had the word continuous growth in it, you would have to use this formula. They took it off the formula sheet, so now it's easier for you because anytime that you need this formula, they'll give it to you and let you use it. So first of all, we'll look at money. And I'll give you these numbers first in part B. If interest is compounded quarterly, that would be our old formula. And 10 years later, $2,000 would be worth $3,453.54. As an idea, what does interest compounded quarterly means? That means every 3 months, they say, this is how much interest you should get in a whole year. We will give you 1/4 of that now. And then the next 3 months later, they say, oh, now you have that extra money. Now this is how much we would give you in a year. We'll give you 1/4 of that now, which is a little bit bigger than the 1/4 they gave you the first time because you've made some interest on your interest. Okay? If it's compounded continuously, the idea, it happens more than every second, but the idea, if we think about it every second, it would be like, this is how much you deserve in a year. In 1 second, you would deserve 1/60th, because 60 seconds in a minute, of 1/60th, because there's 60 minutes in an hour, of 1/24th, because there's 24 hours in a day, of 1/365th. They take that tiny little bit and they say, we give it to you already. And the next second they said, oh, you made a tiny little bit. Now we would owe you this much in the year. But we would take 1 second of that and give it to you right away. And so you're making interest on interest all the time. This number is going to be bigger than this number. But you're in for a surprise. It's not that much bigger. You would think that compounding so many times would be beneficial. It is. But in a 10-year period, it's like $13 difference. So because it's not a huge difference, you'll find that most banks, probably if they're paying you interest, they pay you monthly. If they're charging you interest, they charge you monthly. Partially because of the misconception, if you found out your bank was charging you interest every second, you would get angry and you'd be like, I want to go somewhere else. And they're like, for $13, we don't want to lose customers. It's not worth it for us to charge you interest all the time. So then it's on a thing of monthly. We'll find out that mortgages, they're only allowed to charge interest twice a year in Canada. And we'll look at that as well. So something continuously for money doesn't actually make a huge difference. We are going to, this one's a little bit different. This one's solving for the interest rate. So if we put everything into the formula that we know, and here it has the word continuously, so we're going to use that PERC formula, but again, on an exam, that formula would have been given to you. So now the R is in the exponent. And here's my power. So first of all, can I get that power by itself? Because my life will be easier with logarithms if I can. Yes, I could divide both sides by 200. Now, if the base is e, using the natural log will make your math easier as well, because the natural log of e, which is like log base e of e, is equal to 1. Because log base e of e, if you put a little question mark there and said, e to what power is e, it's equal to 1. So when I take the log of both sides on this question, I would take the natural log of both sides. My exponent would come out in front, and my natural log of e, well, that's just equal to 1. So when I want to get r by itself, all I have to divide by is 3. Now, if you wrote this, and I'll add it in light blue here, if you divide it also by the natural log of e, it will not be wrong. It's just extra stuff that you've written down. You'll get exactly the same answer if you type it into your calculator. You just don't need to type it into your calculator because the natural log of e is 1. But more typical of the PERC formula is using it for populations. I'm going to skip that next question and go to our population question on the back. Again, the ones that I've skipped, you can try them on your own for practice. So population in Vancouver in 1981 was 1.38 million. It's been growing continuously, so they would give you this formula, and they've given us the rate as 1.7%. Find the projected population in 2011, which is 30 years later. So you put in all of your numbers, nothing to do here except type it into your calculator. And then part B, it says, when will the population reach 6 million? So when we plug everything into our formula, we are solving for T. And notice I already wrote my numbers in millions. Can I get my power by itself? Yes. I could divide by 1.38. And now since the base is E, I would take the natural log of both sides. That allows that exponent to come out in front. The natural log of E is just 1. So I could get T by itself. Again, I wrote the natural log of E in green there, saying that if you put that on the bottom, it wouldn't make a difference. Yes.
Where'd you get the 1.3?
So I changed, so in the original question, we're told that we have 1.38 million in 1981. So that would be in our PERT formula, our principal or our starting value. So that's where I got the 1.38 to put into this question. And then these are going to be the most complicated population questions that you will get. And I have one of these on your quiz, and I think I have one of these on your test. So we're looking at a population of some animals. They've got a herd of gophers. It was first studied, there was 15,000. 6 years later, the population was 18,000. This is definitely a PERT question because it's growing continuously. Again, that would be given to you in the question. If the population grows continuously, how long does it take to triple? So if we try to do this directly, we could say, I start with 15,000, triple would be 45,000. E, it doesn't tell me the rate, it doesn't tell me the time. I have a problem. There are two things I don't know in this equation. I don't know the rate, and I want to find the time. I don't know the time either. So if you try to solve this directly, it's actually impossible because there's two things you don't know. So if we want to find the time and we don't know the rate, maybe there's a way to find the rate first. And there is, because they do tell us that in 6 years it goes from 15,000 to 18,000. So 15,000 to 18,000 in 6 years lets me set up this equation. Can I get the power by itself? Yes, I could divide both sides by 15,000. And then I could use natural logs, and I could solve. And notice that I've got like the dot, dot, dot after the R, because I keep all of the decimal places. If we round early, we have the potential that our answer is going to be off by a certain number of decimal places, and that's going to be a problem. Now that I have R, now I can solve for T. Now, It doesn't matter if you use the 15,000 or the 18,000, because if it's going to triple, when you get your power, here's my power. When I get my power all by itself, I'm going to get a 3, because it's tripling. If you used 18,000 to 54,000, and you simplified, you'd get a 3 that way as well. Now I can take the natural log of both sides. Again, I've got the dot, dot, dot saying I'm using all my decimal places. And I solve for t and get 36.15 years. Now, I made a grammatical mistake in this question on purpose to see if anybody could catch it. In the wording of this question, there's one word that is wrong. What word is it? Any guesses? A crash of rhinos. So try this one on your own. I'll put the answer up in a bit, and I'm also going to hand back your tests so you can look over them. 28.56 is the answer for